Well, next we have Tom McDermott, inside DG, current president of Texas Packet Radio Society. By the way, Tom, congratulations. This is your second year as president.
That's right.
And then as we started, we were there back in '84. He'll be talking about the FHSS radio design, TAPR sponsoring, along with the Texas Packet Radio Society here.
Thanks, Greg. This talk will be kind of an in-depth discussion of a particular design. One of the problems, of course, you have when you do a design as amateurs is you have to use chips that somebody else invented, and that puts some severe limitations on all the neat stuff you can do. Well, I'll talk about briefly the design objectives, a little bit of the system level requirements. I'll go through an analysis of the system level performance and look at the implementation of this slow hop frequency hop radio, and go into a few of the interesting implementation details. Three of us, Bob Stricklin, Bill Reed, and I got together a couple of times to talk about what should the design objectives of a frequency hop radio for the amateur do. And we kind of mulled over options, and then we looked at about 10,000 newsgroup postings and sorted through all of those. And kind of came up with a subset of what we thought the design objectives would be based upon what people seem to be asking for. The first one is to provide fairly high-speed throughput compared to what we have today, 1200 baud, 9600 baud. And so our objective was to get something like ISDM throughput, around 128 kilobits per second. There are some options for greater throughput. I doubt they'll be available in the first release of the code, so there'll be subsequent releases. The second objective was to try and provide a path length of 20 miles. Most of the comments we've seen from people is that they'd like to try and get longer path lengths than 2-3 miles out of one of these systems if possible. The third is we dedicated this radio basically to handle Internet Protocol frames. Its whole purpose in life is to move IP frames. So it's a little bit single-minded in that regard. And then minimal disruption of existing users, should say 902 to 928 megahertz. We elected to put it in the 900 megahertz band for a couple of reasons. Number one is that there's already a number of existing Part 15 devices there, and we felt there would be the fewest number of amateurs who would have their aux gored by us putting a product in the band. Consistent with having the frequency low enough, we can actually get a 20-mile path with antennas and feed line that most amateurs would actually be able to implement. And so we elected to put it in the 900 meg band. We'd like to accommodate a reasonable number of simultaneous users, but reasonable is not as large a number as we might desire. How large? Well, we have 43 channels, and we're trying to build hubs that will take up to about 8 or 10 simultaneous users. That's in the multi-point configuration. One of the things we tried to do is, in looking at past packet radio projects, a lot of work has gone on to building point-to-point links, but it really hadn't addressed a lot of the networking problems hams really seem to have, which has to do with how do you build a node that allows simultaneous users to access one good site? How do you provide connectivity of that one good site to an information service that might not be available to the building? We wanted to try and build in some hooks and handles that would make the networking of these radios a little bit easier. The interface to the computers over the Ethernet, that was done because we feel we finally got to the point with things like Windows 95 and NT and Linux that it's actually maybe easier to hook a TCP/IP stack up to a radio through an Ethernet than it would be any other interface. In the future, we'd like to add a IP router into the radio. The radio has sufficient processing capability to do this, and we're in discussions with Phil on the use of his stack, maybe porting his stack over to the radio. One of the first choices we made was to go time division half duplex, and the reason for that is cost and simplicity. In a previous packet system like TextNet, we put in single antennas, single feed lines, and we avoided the use of duplexers and other devices. So we operate half duplex to try and minimize a lot of the antenna infrastructure costs and the RF stuff. We elected to have the radio transmit for 10 milliseconds and then receive for 10 milliseconds. And we have to essentially have a fairly fast TR switching, so it's obviously a solid-state TR switch. And within 10 milliseconds, we have to do a lot of things. And this pretty much determines the throughput of the radio, is how fast we can acquire carrier synchronization in a 10 millisecond period. Normally in what we call mode 0, the time slots alternate between transmit and receive. So it just bounces back and forth between transmit and receive. However, there are times, especially with TCP IP traffic, where the traffic is asymmetrical. If you do an FTP, you may send not very many bytes to the far end to download a file, and you get a large download, same with HTTP traffic. And so we wanted to have an option to go into an asymmetrical mode where you may transmit a short time and receive a number of consecutive receive frames, which potentially doubles the throughput of a radio. Yes? No, we'll go into that in detail later on. To look at throughput, we chose to use a QPSK modulation format, and the modulation rate is 300 kilosymbols per second. We may up this slightly because of the exact SAW filter that we happen to be able to acquire, but this was the rate, happens to match some of the clock rates we have on the module, and so it's an efficient implementation. We transmit at 300 kilosymbols per second, which means that the raw bit rate would be 2 bits per symbol, or 600 kilobits per second. As we'll see, we throw away a lot of those further on. So in mode 0, essentially, the radio transmits for 10 milliseconds, receives for 10 milliseconds, transmits, receives, and just goes on through that pattern. In mode 0, we employ forward error correction, which means that half of the bits are overhead related to forward error correction, and so the effective user data rate is half of 600 kilobits per second times half of the transmit density, so it's about a quarter of the actual raw bit rate. These other two modes are for asymmetrical traffic, where the transmitter will transmit for 11 consecutive times and then receive for 1 symbol time, and the receiver does the opposite. In this mode, we also run the forward error corrector at rate 1/2. We also have a mode, it's built into one of the chips, where we can puncture the code up to a rate 7/8. We lose a little bit of system gain, but we gain some throughput. In this case, we also transmit 11 and receive 0. We picked 11 because we can get exactly 2 maximum length Ethernet IP frames into a single transmission when we do that. One thing that should be noted, the frequency hopper is actually hopping channels each 10 milliseconds. So it's not sitting on one channel for 110 milliseconds. It's actually going to be on 11 different channels during that time. We periodically have to have a reverse channel back so that the receiver can tell the transmitter about the progress and the value of the frames received during each of these transmission times. So even though we're transmitting continuously, we'll be hopping each of those times. We picked 10 milliseconds because it pretty much came out of thin air, but the rationale that we like to explain is that we think it's not going to open a squelch on an FM repeater. So we hope it's short enough that it doesn't actually. It shouldn't anyway. With a 300 kilosymbol per second modulation rate, the spectral characteristics of the emitted signal are going to be so noise-like that no squelch is going to open up on it anyways. But at 10 milliseconds, it's sufficiently fast that we felt it would be reasonably difficult to find for the average amateur. So we'll go through some throughput calculations. In mode 0, which is where we transmit half the time and receive half the time, the raw bit rate is 600 kilobits per second. And because we're running at rate 1/2 coder, the actual user portion of those data bits are half of that total. Then we're only transmitting half the time and we're receiving half the time, so the throughput gets knocked down by another factor of 1/2. And then, as we'll see in the detailed timing at the end of the presentation, there's some overhead inside those 10 millisecond time slots to get the receiver synchronized. And so the throughput is actually about the effective data time of a 10 millisecond frame is about 8.83 milliseconds. And that results in the following throughputs, assuming that we don't have errors on the channel, of 132 kilobits per second in mode 0, 242 in mode 1, and about 425 kilobits per second in mode 2. I guess this is what you call the optimism slide. You can't do better than this. It's pretty useful to have a hub function, and that is, we envision one of the applications of this radio is to put it up at a tall site that ideally has internet access, hook an internet connection into this hub, and then anybody with a terminal can get on and essentially have ISDN speed internet access from their computer, whether it's at home, in their car, or whatever. There's also a case, as we'll see, that you might have a good site that doesn't have internet access, and so we have a second application for that. One of the advantages of using time division half duplex is we assign one of the radios as the control radio, and it outputs a timing mark to all of the other radios, so that all the radios in a node, and we can have up to 6 or 7 of these, maybe 10 of these radios, we don't know the number yet. They all transmit at the same time, they all receive at the same time. Which means that we can passively combine the power output of the transmitters, and on receive we can passively split. And then we have to have a little bit of TR switching and a PA to make up for the losses of the passive combiner splitter. One of the difficulties when you combine a number of radios is that your PA needs to be very linear because you're summing a number of carriers. So the peak to average ratio is in fact very high. And so even with a total of maybe 8 or 10 watts, you're probably going to need a PA that's linear up in the several hundred watt range in order to achieve good throughput. You also need a filter and receiver, but the same TR switching signal that slaves all the radios comes out here and runs the TR switches on the PA, the combiner. So what it allows us to do is to build a node by taking a radio and plugging it into a box that sits between the antenna and the radio, and gives us the ability to have multiple users access this device and still not have to get into a real complicated scheme. The benefit of this is that if you have a point-to-point link or you don't want a hub, you just don't implement all of this stuff over here, and so it's a minimal cost for a point-to-point link. So we try to kind of optimize the cost while still providing hubbing function, but you have to implement this RF hardware to do it. The PA can be done in a number of ways. I don't think it's that difficult to switch a solid-state PA that quickly. I could be wrong. Yes. If you try it, yes, it's not really designed for hub-to-hub interconnect. But there are a couple of interesting applications. One is that you may have your internet connection a far distance away from the hub, and so you can assign one of the channels, radio channels, to provide that link back while you have the user channel. In order to use this, the user has to come up and synchronize with the control channel. The control channel then assigns one of the user channels and the particular hopping sequence between the user and the node so that they don't collide with each other. And then the control channel picks the sequences for the other channels so that they stay out of each other's hair. So we felt it was the simplest hardware mechanism that we could come up with to build a multi-channel node. There's a couple of options. One is to have a spreading sequence. It's the same for all the radios, but they start at different offset times so that they kind of leapfrog each other around. And there's a couple of different ways to do that also, some of which have desirable properties. If the radio channels are assigned in a sequence where they're used monotonically, you can prevent any collisions whatsoever, but then you don't have as good statistical properties in the way that you do the hopping. Yes. We looked at it. The equipment that we've seen that does that doesn't work very well. In multi-point configurations, it's possible. As we say, it's only software. Okay. However, there may be some practical problems. It's something we can look at to do. Most of the implementations that I've seen have suffered from some fairly fatal problems, so that when you multi-point hub a single radio, the actual throughput drops almost immediately by a factor of 10. Okay, in which case we're back to 9600 baud radio, and why bother to go through the exercise? So, yes. Yeah, the other modes cannot be used in a hub function. You're restricted to mode 0 when you have a hub. That's correct. I guess we could say that was intentional, although it's not, because it allows us to effectively share the internet bandwidth amongst all the users in an equitable way, whether that's intelligent to do or not. It would force them all to get about the same allocation of the channel. Okay, looking at the radio design in particular, our assumptions: transmit output power is 1 watt. This is done so we avoid having to do active power control on the transmitter for the current regulations. I assumed we could build an antenna with a gain of 6 dB at the hub site. An omnidirectional 6 dB gain antenna is quite feasible. 3 dB of cable loss I assume a receiver antenna temperature of about 293 Kelvin. The receiver would have 8 dB gain antenna. Since it's probably pointed at a hub, it's a little easier to get more gain. Again, 3 dB of cable loss. The center frequency is 915 megahertz. The bandwidth of the receiver is 600 kilohertz. And the noise figure is 8 dB. Actual, the computed noise figure is 7.8 something. If we do that calculation, of course, we have 2 watts of transmitted power because we got 1 watt and we got 3 dB total gain after you subtract out the feed line loss. The receiver noise temperature is calculated about 438 Kelvin. And this yields a signal-to-noise ratio at the receiver of plus 21.1 dB, which is, for QPSK modulation, an EBNO of 18.1 dB. That sounds pretty good so far, but this is at a range of 20 miles. As you can see, there's not a lot of room left over with a 1 watt radio. You're operating pretty close to what you can do at 20 miles with 1 watt. This is free space. If you get into urban conditions where Barry McCarnan had a good talk yesterday about path loss in urban areas. The path loss goes up a lot faster in urban areas, and the range is going to be less. If we look at the kind of energy per bit divided by the noise power density that we need for BPSK or QPSK, a bit error rate of 10 to the minus 6 requires about 10.5 dB EBNO. A bit error rate of 10 to the minus 9th requires about plus 12.5 dB of EBNO. And that's this point down on the curve. At 10 to the minus 9th, it requires about 12.5 dB. As you can see, we're already, for 10 to the minus 9th, 1 to about 3 dB better than FSK at this point by using QPSK or BPSK modulation. Now, one of the things we have to do is differentially code the data. I may have the wrong factor here. I'll ask Phil. The QPSK data, we actually code the difference between a pair of bits rather than the bits themselves. You lose performance because you have some error multiplication when you do that. And so if you take an error on one bit, it can cause you to incorrectly decode the next bit. And so when you differentially code bits, you lose some loss. I'm not sure if that's a correct 2.3 dB factor or not. There's a factor for the amount of equivalent EBNO that you lose for chaining the calculations. And 2.3 may or may not be the right.
There's actually 2 things there. There's the error propagation.
Right.
Actually, soft position code is actually not that much. But the error factor can be differentially decoded.
Yes.
It's a different curve. It's exponential rather than a Gaussian.
Mm-hmm. Yeah, we have a coherent. Right, we have a coherent demodulator.
That's not that bad.
Okay, so 2.3 is a little bit too conservative an estimate here. So let's go through the available implementation. We have available an EBNO of plus 18.1 dB at 20 miles. We need, at 10 to the minus 6, we need about plus 12.8, which would yield a raw implementation margin of about 5.3 dB. That's not a lot of implementation margin. We can improve the requirement for EBNO by using forward error correction. We have in the radio convolutional coder using 3-bit soft decision decoding, and that the needed EBNO at a rate 1/2 coder at 10 to the minus 6 is about 5.1 dB, but we lose some for this differential coding. At rate 7/8 we need a stronger signal, but we lose again some from the differential coding. So the implementation margin, if you assume this is a little bit too conservative, is slightly better than 10.7 dB at rate 1/2 coding, or slightly better than 9.1 dB. To me, this is fairly practical. It says that theoretically we could work with 100 milliwatts at 20 miles with no implementation margin whatsoever. Or in a practical case, 10 dB implementation margin assures that we're going to have some reasonable amount of performance at 20 miles. We talked about needing 3 dB of feed line loss. At 900 megahertz, 3 dB of feed line loss corresponds to a pigtail using RG58. It's about 50 feet of RGA, and it's maybe 60, 70 feet of 9913. So you're not talking about a lot of feed line to the antenna here, which means in a hub site, for example, that's good. You put the radio up on the top of the building, try and keep the feed line short. But at 915 megahertz, you got to worry about feed line loss. You got to worry about antenna gain. You got to worry about trees, because trees have a lot of path attenuation, especially pine trees. Well, we don't have those in Texas, so that's not a problem. You're right. You're right. Somebody said, "What's the difference what's the difference in Texas between a tree and a shrub?" About 1.5 feet. Okay. The RF portion of this I talked a little bit about during the talk yesterday. The TR switch is a solid state device. I think it's made by HP. It handles 1 watt. It's a neat little 8-pin device, and it's easier than trying to actually string out pin diodes and all that, or Schottky diodes. Schottky diodes also make good TR switches if you do it right. We go into a 915 megahertz filter. This is one of these little Toco three-section helical resonator filters, very small, very cost-effective. It's designed, it turns out to exactly the specifications we had in mind. So another way of saying that is we found the filter that would work and we respecified the radio to match it. The output of the filter, and this is needed because there is a lot of strong out-of-band stuff just above 928 megahertz band. There's a lot of paging systems, and so we need a good RF filter to knock all that out-of-band stuff down. It goes into a low-noise amplifier. There is a single chip that's a combination of a low-noise amplifier and a mixer made by Motorola for 900 megahertz devices. So we were able to get those two functions into a single IC. The LNA has, think about 4 dB noise figure, 4 to 5 dB noise figure, and about 22, 23 dB conversion gain. The nice thing about having a solid state is we can get a lot of gain in this mixer function instead of having loss. So essentially we have, at this point, 2 active devices in the path. At this point we've been down converted to 85.35 megahertz and we go through a SAW filter. The number of SAW filters we had available off the shelf was relatively limited, and we picked one that looked pretty good. It had 2 attributes. Number one, it was 600 kilohertz wide, which is about the widest one we could find. Number two, its group delay was very well controlled. It had excellent group delay across the passband, meaning we could use most of that 600 kilohertz for our desired signal without causing differential delay across the filter. So we come out here at a 600 kilohertz wide filtered 85 megahertz IF signal. That goes into this complex up and down. This is a single IC made by Harris. The first thing we do when we hit that is we go through 80 dB of limiting. The device has a couple of limiter stages. When the input signal is almost non-existent, at this point, 0.9 microvolts. In the 600 kilohertz bandwidth, that's equivalent to the noise across a resistor room temperature. We go into, and we have essentially no limiting. We're operating in a limiterless mode. And that's good because the performance of QPSK is much better when you don't have limiting in the input side. As the signal kicks up in strength, we'll start kicking in limiting. Limiting will start to gradually occur as the signal strength goes up. That's desirable because when you get to real strong input signal and you're using a lot of limiting and you lose a little bit of performance, it doesn't matter because you get a strong signal anyway. So setting the limiting, the onset of limiting is important to preserving the performance of the demodulator. You ideally want a linear channel. Bill was giving me a good explanation of this last night. You ideally want a linear channel until the EBNO gets up into the 25, 30 dB range, at which point the onset of limiting doesn't really hurt you very much. The down converter is fed by a quadrature oscillator. What we actually have here is a local oscillator operating at 170 megahertz, and this particular chip takes it, divides by 2, and generates the quadrature signals to mix the output automatically, so it's the crystal oscillator. That produces the in-phase and quadrature phase, which is what we get by taking this signal and mixing it with the sine and mixing it with the cosine to produce the 2 outputs. Those are baseband outputs, we hope. Actually, they'll be slightly off frequency because nothing we've done at this point in this radio has actually established the exact frequency difference between the transmitter and the receiver. So we could have, in fact, a frequency error. If transmitter and receiver happen to be off frequency by a kilohertz, what we're in fact going to have here is a baseband signal, but it's going to be rotating at a 1 kilohertz error rate. In the transmit direction, we have 2 analog signals, I and Q, which are baseband, and fortunately these are exactly at baseband 0. They don't have a frequency offset. We mix them up using these same 2 signals to 85 megahertz. Now we don't have an IF filter on this line, and the reason is when we generate these 2 signals, they've been low-pass filtered with a root raised cosine filters, so they have nice spectral properties already. They fall off, and we'll look at that in a later slide. So in fact, we have a well-controlled IF spectrum shape at this point. We mix it up to 950 megahertz, and we run it through a filter. The reason we run it through a filter is to reject the image. If we didn't have a filter here, we would put the 950 megahertz and the image into the PA, and we'd burn half of the PA's output power on the wrong signal. We could then filter it off after the PA, but from an efficiency point of view, it's better to put the filter in front of the PA instead of after the PA. The power amplifier is a 1 watt part that Maxim just came out with. It has to be run in the linear mode. The reason it has to be run in the linear mode is that the nice spectral shape we achieved by baseband filtering these things is destroyed when you hard limit a QPSK signal. So if you hard limit a QPSK signal, you instantly generate sidebands right back again that you spend all this work trying to get rid of. So you want an entirely linear transmitter from baseband all the way out to the RF channel. And so we have carefully designed a linear system. We'll find out how linear it is when we put power to it for the first time. Up to this point, this looks just exactly like a channelized radio. The thing that makes it a frequency hopper is that we change the local oscillator frequency here each 10 milliseconds. The hoppers are phase lock loop VCOs. They're programmed. There's a PIC chip that rides up on this board, which is a single chip microprocessor that communicates with the synthesizers here and tells them what's the next channel to go hop onto. The VCOs require just under 9 milliseconds to achieve frequency lock within, looking at the control voltage, something like 0.01 microvolts, I think. And so that turns out to be a negligible frequency error. So we have to have two VCOs, one of which is slewing to the correct frequency while the other one's being used. If not, we would have to go to a frequency, turn on the hopper, wait for 10 milliseconds or 8 milliseconds, then we could use the channel. We don't want to waste that 8 milliseconds. And so this guy is getting set up for the next frequency while we're using this one, and then we flip the switch and use this one and go back and immediately reprogram that one. So it starts slewing its way up to the correct frequency. We need good isolation in this switch here, because if you don't have good isolation, what you get is the desired frequency and this low level thing swishing through as it decides to settle on frequency. Yes, John? PLL VCOs were lots cheaper, and we could achieve the programming accuracy and the speed and directly generate these at the desired RF frequency with a very simple scalar chip and a synthesizer chip. So it was vastly lower in cost and vastly simpler to implement. DDS is good, but you're limited to the maximum frequency you can directly generate out of a DDS. You have to then mix that up. We looked at a DDS design, and we required, the best we could do with the available chips was a 5-band design, where the DDS could cover about 1/5 of the hopping bandwidth, and we had to mix it with one of 5 different local oscillators, depending on where we were. So the complexity got to be large. If we had a DDS chip with a clock rate of, say, 2.5 to 3 gigahertz, we could do it directly with a DDS, and but we haven't got one of those. When I find one, the first people that want to know are probably right down the street here at the NSA. Yes, sir. Yeah, this device, I think, was about 60 dB of isolation, and I recall, I forget, Bob, do you remember what that part is? Yeah, the VCO switch. Okay, it's a Harris. I think it's a transistor solid state switch. It's not a pin diode switch. So it actually it's got a little bit of gain in the on position, and it's cut off in the back position. Then you have to look through the reverse leakage. But it's an actual series shunt switch. So you get isolation from the shunt path and the series path, which essentially doubles the isolation going back to the switch. Now, the switch is designed for fairly high isolation. It was like a $2 part, so it was a good design choice. Yes, Barry? I don't have the specs with me on the filter. It's a 3-section helical, and it's out of band plus or minus 20 megahertz. It's down like 30 dB or something, 25 dB, something like that. Toco America has a website. You can go up and look at the filter specs on the website. And I forget the name of it. It's tocoam.org or something, or .com, something like that. But just do a web search on Toco America, and they've got all the different filters, both the SAW filters and the helical resonator filters up on the website. The whole data book's up there basically, and you can get the exact filter details. Yeah, it's also a Toco part. This is the other board, mostly digital. The interfaces at this point here are analog. One of the reasons we put analog interfaces there was so that we could loop back the I and the Q at analog when we're trying to debug this thing. So we can kind of separate out our baseband problems from our RF problems. And the second thing is when we're testing the RF deck, of course we can just put DC into the I and Q inputs of the RF deck, and we can generate CW carriers out the output, so we can test all the stages going up and down the RF thing without having to have modulation on it. So from a trying to debug this thing point of view, having an interface right there is kind of convenient. It's I suppose you could come out with a final version of twin large board, but it make it so we can test it.
That was one of our marketing points, a really expensive CW.
There you go. There you go. Well, since you have I and Q, you could also call it a single sideband exciter and single sideband receiver and all that stuff. Geez, I hope no one uses it for that. On the receive side, you have to receive the I and the Q samples. One of the things you got to do when you're operating up in the 300 kilosymbol per second rate is trying to oversample the input waveforms is pretty tough to do, because if you oversample, you have to process a lot of samples. And so the A to D converters are actually clocked off the recovered symbol timing clock. We know approximately the frequency of the symbol timing clock, and I'll go into later how we do that. The symbol timing, it turns out, is not done inside this DMOD, and we have a PIC chip that does an oscillator function to derive that timing relationship and zero in a correct phase relationship. Once we sample these guys at the right time, which is 600 kilosample per second rate, it's twice the carrier rate, the samples are fed in 10 bits I and 10 bits Q in parallel into the QPSK DMOD. I'll talk a little bit later about what's in this box. It's a Harris part. It's a marvelous chip. It's got gobs of stuff in it, and it's all digital. The output of this are soft decision I and Q data streams. 3 bits on the I, 3 bits on the Q, at 300 kilosymbols per second. Those go into the convolutional FEC decoder, which removes the rate 1/2 code or the rate 7/8 code if it's in mode 2, and comes out with a raw data stream. Now, one of the hacks that we did here, because it's efficient, the Motorola 68360 on it has an HDLC channel. The HDLC channel uses DMAs that are in the chip, and so at the kind of rate that we're running data, from the software point of view, we can tell the HDLC controller, here's where a bunch of frames are in memory, go send them out when we tell you to send them out. And it'll automatically chain the buffers and things like that. So it'll grab them from the memory, send them out the port, quit, stop, wait. We can chain them on the receive side. A lot of this is handled in hardware. So what we do actually is generate an HDLC frame, which has got a bunch of flags, the data, a CRC, more flags, just like AX25, except we don't put exactly AX25 in the header. We put our proprietary radio communications protocol up in the first 16 bytes of the header. And this is what's sent and received. The advantage of it is it's simple and it's fairly inexpensive. It doesn't require any hardware. The disadvantage is that if you lose a significant number of bits in that frame, the frame is gone. So the forward error correction in this case provides us performance gain in a Gaussian noise environment. But if there's a strong interfering carrier on the channel that only lasts for a few microseconds, it's got a good probability of taking out this frame. And so we can lose this entire frame of data. As Phil was talking about before, we could interleave all of this stuff and come out with a way to write through this. We have to look at the characteristics of the interference. If the interference is like an FM paging transmitter or an FM data source, it's going to be on the frequency the whole 10 milliseconds, and then anything we do is going to lose that whole amount of information anyway. If that's only one frame out of N, we may be able to get around it. We had a simpler approach, and that was if we lost a frame, we'd transmit it on a later hop and try and pick it back up. So it's simple. We may, in the future, if we can find a way to chain frames out of this device without the HDLC controller under software control, we may come up with some more sophisticated algorithm in mode 0. We'll probably just use the dumb and simple method to get it out. Yes. Yeah, it does bit stuffing. It's just it's a standard HDLC controller. It's right on. We use that because on the receive side, it makes kind of all of the modulation and forward error correction and stuff kind of turns invisible. And so the HDLC channel thinks it's just seeing another HDLC stream from the other end. It's just that the probability of errors in that HDLC stream are improved because we're using forward error correction on an additive white Gaussian noise channel. It's straightforward. It's not necessarily optimum, but to do this any other way would require probably some custom frame generation hardware in here. We're trying to avoid putting many more parts on the board. We have an Ethernet interface to the 10 base T, and of course the purpose of this is to get all these frames from the internet queued up into the processor so they can be sent out the HDLC channel. Now we have to segment the frames. An IP frame can be 1,500 bytes long when it comes in on an Ethernet interface. 1,500 bytes doesn't fit into a 10 millisecond channel. It turns out it can take up to 6 10 millisecond time slots to send a single 1,500 byte frame. So one of the things that the radio overhead does is it has a segmentation reassembly function built into it. So it will take apart a 1,500 byte frame. It will send it in different slots and different hops. It reassembles it and redelivers it as a packaged IP frame at the other end. In the mode 1 and mode 2, we have enough time we can get 2 of those maximum length IP frames through in a single transmission time. Most of the time, however, an average IP frame is between 280 and 305 bytes. That's what Cisco tells me on the internet today. It's been going up with time. It was 280 2 years ago, and its average is up to about 305 bytes now. A maximum length Ethernet frame is 1,560 bytes. Okay, so 280 byte frame, it turns out will just fit, we believe, inside one of these 10 millisecond slots. That's an average. That's right. It's very bimodal. At any rate, we have to segment and reassemble frames in the radio. So there's a protocol for communicating the segmentation and reassembly, and it puts a little sequence number on them so it can put them together at the far end. So there's a lot of concessions to trying to simplify the hardware that we have to run in sake of simplicity. The other thing to note here is that there's no EEPROM on this radio. It's flash only. One of the purposes is we want to put a MAC layer interface in it so that you can reprogram the flash through the interface. One of the things we want to do with this radio is encourage future software development. We're going to come out with a version of 1.0 that's kind of simple-minded but gets the job done. You know, try and have people help us write later versions of the code. And so the easiest way we thought to do that was to not have EEPROM in it at all. It seems like every time we've had EEPROMs in something, we've had programming problems, we've had supply problems, we've had cockpit problems. So we'll put flash in, which allows us to completely destroy the bootloader in it and result in a totally dead radio instead of a partially dead radio.
Are you going to do extra AC ports, do extra sticker ports coming out so you can basically do a wide area site? No, we'll use a 10 base T Ethernet hub. There's one port coming out the radio, and that's one 10 base T. That's it. It's far more useful. I just think about buying that board for those little just that header was there for those extra AC ports. Don't worry about that big C and anything.
Right, but then you'd have to strip all those chips off, and this thing becomes a multi-purpose processor board, and it's probably easier just to go off and invent your own.
Yeah,
so, there's a number of timer channels and other things that get tied up in this. We didn't feel it was worthwhile to invent yet another new computer, since there's any number of sources of those things. The modulator is a Motorola part. The Motorola part is pretty slick. I've got a diagram of it later on. It contains a phase lock loop, so you can phase lock a couple of digital FIR filters inside of it to a multiple of the symbol rate. And those FIR filters provide a 0.4 root-raised cosine roll-off factor after differential encoding, and then those go to a pair of D to A converters. So essentially it's got a differential encoder, two filters, two D to A's, and a single package. It's a pretty nice device. No, not in here. That will come with further documentation. We have to do some testing on the radio and building the hardware. Once we get things working and we have assured source of supply of parts, well, more information will be forthcoming. So what we have here is a nice paper design, but it's not working hardware yet. It turns out that this Motorola part has a root-raised cosine roll-off of 0.4, whereas the Harris part implements a root-raised cosine roll-off of 0.5. And neither of those can be altered. It turns out that the error, inter-symbol interference error, due to that amount of mismatch is very small. It's about 28 dB down from the symbol value, so it turns out to be pretty negligible in the overall performance. Yes? No, the flash is, the software here is accessible from this direction. Now, if somebody in the internet knew how to get to this thing and hack it, I suppose that's possible. That's controlled by the SMOS, simply a matter of software. That means if we write good anti-hacking code, the answer is no.
On the current page, that seems to be speed 5 to be operated in BPSK mode.
Yeah.
And we put a receive converter that's going to go from 77 to a band. That could be for projectile link on this.
Yeah, the QPSK D mod, I think, is programmable to receive in the BPSK mode. Okay, there's some configuration bits. I didn't bring the Harris manual with me, but I think there's a couple of bits that will allow you to alter the way that the carrier phase timing is recovered in the device. So I think that you can, in fact, switch it to BPSK mode. Yeah, the flash, I think some of the flashes have a protected boot block mode in them that you can write a bootloader in, and to overwrite that very front-end section of the flash, the processor can do it, but it has to do a lot of really strange stuff to do it. The theory being that the software is not likely to run away in some crazy mode that's going to overwrite the bootloader. And by having that bootloader done, we should be able to flip a switch and then be able to download the Mac or put in some very sophisticated pattern recognition so that over the internet we could download new code. One of the ideas behind having that Ethernet interface directly tied into the processor is that, like after the paper yesterday on SNMP would be a good management protocol for the processor part of this radio. Since that's connected on the internet side, you can use SNMP to get to that. And so the paper yesterday I thought was good because it kind of brought up a novel idea we hadn't really thought about. So there's a number of performance. One of the advantages of having an internet connection on that side is that you essentially have the ability to download the radio over the internet. You have control of the parameters. If you have it at a remote site, but it has internet access, then theoretically you have a lot of control over this radio that ordinarily would be pretty tough to get to otherwise. Looking at the receiver front end in a little more detail. The first thing that we go through is a TR switch. Now the TR switch has about a dB of loss. And then we go through this three helical resonator filter, which has 2 dB of loss. And so for the first stage up to 0.1, which is filtering the TR switch, we have a gain of negative 3 dB. So we've taken a 3 dB hit and we haven't even hit an active device yet. And the output power, assuming an input power of minus 108 dBm, which is 0.9 microvolts at 50 ohms. 0.9 microvolts doesn't sound like good sensitivity compared to an FM radio that's 20 kilohertz wide. But 600 kilohertz wide radio, that's pretty good. So its output level will be minus 111. The second stage is the low noise amplifier mixer. It has a noise figure of 5.5 dB and has 28 dB of gain. So the output power is minus 83 at 0.2. The SAW filter has 15 dB of loss, so the output drops down to minus 98 at 0.3, and we have a post amp to take that back up to minus 80. Minus 80 is the input, is the minimum input received signal level to the IF processing device. So this gets us on the weakest received signal up to the minimum input level. As we go up above received signal, we have enough linearity in this amplifier and in the LNA to behave gracefully. As we get above a certain receive strength, then the limiter on the receive side starts to kick in. Anyway, if you go through this computation, you'll find that the cascaded noise figure of this receiver is 7.84 dB, and that sets the received performance. And that's at a temperature of 25 Celsius and a 650 kilohertz bandwidth. So this is basically, if we have a 0.9 microvolt signal, we've got 0 dB signal-to-noise ratio, which is minus 3 dB EBNO for QPSK. Yeah, that gives you a feel for the kind of signal levels we're going to take to get into the plus 20 dB range. It's going to have to be 20 dB hotter than 0.9 microvolts. Yes. Well, not quite. It's a little better according to my HP tool that calculates these things. I thought it was a little bit off also, but I talked to the guy and he said no, it should be a little higher. So I'm no expert in noise figure. You think we're optimistic by a dB? By 3 dB? Yeah, you should see 8.5 dB right there. Right, so this maybe should be 8.84 instead of 7.84. There may be a bug in the tool. Okay, this comes out of an HP tool for doing this noise figure analysis, where you put in all the intercept points, and we'll have to go look at the tool. There could be a bug in that tool. In fact, this is actually cut and pasted right out of the tool. So this may be 8.84 instead of 7.84. So we may have a dB error in the received calculation. Something we need to go check. As we said before, frequency hopping is achieved by altering the local oscillator frequency. Because if we don't do that, what we have is a non-frequency hop radio or a channelized radio. And of course, the key issue is the settling time of those VCOs. Since we change every 10 milliseconds, if we had one VCO, we would have to settle a whole lot faster than 10 milliseconds. That's tough. 2 VCOs gives us 10. If we had 3 VCOs, we'd have 20 milliseconds to settle it. But the simulations that we run on the VCOs get us there in just under 9 milliseconds to a very tight frequency range. One of the other things we did is we looked at the amount of noise. VCOs have 1 over F noise. 1 over F noise is very destructive to PSK radios. In integrating the 1 over F noise curve of the VCOs that we could get, there was about 10 dB of margin over the 1.5 degrees RMS noise point. So we set an arbitrary limit of 1.5 degrees RMS noise out of the VCOs as to what we wanted to keep it down to, and the VCOs that we were able to buy off the shelf were 10 dB better than that in their total integrated 1 over F noise in the bandwidth. So our feeling is we have a fair amount of margin in the VCO noise and it meets the manufacturer's spec. Interestingly enough, this is a case where going slower is harder to do. The lower the data rate of a PSK radio, the worse the 1 over F noise problem becomes, because you're very much closer to the carrier frequency of the VCO. You have a lot more 1 over F noise. And so in fact, there's kind of a minimum data rate that you want to run a PSK radio at if you have noisy oscillators. Commercially, it drives the microwave guys nuts. Now, if we transmit this spectrum without filtering, then what we end up with is a spectrum between the first nulls of twice the symbol rate, 300 kilosymbols per second at 600 kilohertz wide. And then, of course, we get the sine x over x distribution, so the next peak is minus 13 dB from the central peak, and on it goes. If we run this through, if we low-pass filter the baseband signal before we modulate the output with what's called an alpha equals 1 filter, then it turns out essentially we have a spectrum that just throws away all this stuff outside the Nyquist point. And so we have, the channel rate, so we don't have any out of channel spectrum. And in fact, we can use narrower filters than an alpha equals 1, but it causes the zero crossings of the waveform to drift back and forth, or to jitter back and forth, but they jitter symmetrically. And so in fact, the actual transmitted spectrum is less than channel bandwidth by the alpha factor. So the width here will be 1 plus alpha times the symbol rate. So if we had an alpha equals 0, this would be half the width of that. Building alpha equals 0 filters is a difficult thing to do. You require FIR filters of essentially infinite length, and you have no tolerance to mistiming anywhere, so it becomes very tough. Reality is alpha factors in the 0.3 range or 0.25 to 0.3 range are kind of state-of-the-art. 0.4 is more easily achievable. That means our RF bandwidth is 420 kilohertz, and if things work out right, it means we might be able to jack up the data rate of the radio a little bit, but we're going to sit where we are now just because of the clocks we happen to have on a particular design. But theoretically, since we have a 600 kilohertz wide filter, we could increase the data rate by the ratio of 600 to 420. The point here is that low alpha raised cosine filters narrow the emission bandwidth, minimize the interference on adjacent channels. That's useful in a frequency hopper. If you happen to have several hoppers and they happen to hit adjacent channels, you'd like them not to interfere with one another. So it's desirable to do that. But also it just puts out less RF on undesired frequencies, which we're going to throw away anyway on the receive side since we're going through a SAW filter. We might as well put all that energy on desired frequencies rather than on undesired frequencies. Now if you take a filtered signal like this and you run it through a Class C amplifier, what you get is that. Okay? And so you have to run Class A in the transmitter if you want to preserve the spectral shape. That's one of the drawbacks of QPSK, is that you have to use Class A or Class AB amplifiers. So David Letterman has a top 10 list. I've got a top 3. There's only 3 problems: speed, speed, and speed. The VCO lockup time, speed is one problem, and of course we solve that using multiple VCOs. The next problem, we'll get into this here in some detail, is the carrier recovery lockup time. Each hop, each 10 millisecond hop, we have to reacquire a carrier lock. We do this in about 800 microseconds is our estimate right now. Even when we're transmitting continuously but we're hopping channels, we have to reacquire carrier lock because we have a fully coherent demodulator. But we have a trick that we can utilize. We don't know the exact frequency of the transmitter or receiver, but during the link establishment process, which can take a couple of seconds, the receiver computes the frequency error of the transmitter. Since it acquires carrier lock, it knows exactly the frequency difference between the transmitter and receiver because that's the frequency it has to rotate the received signal at in order to acquire carrier lock. So we memorize that frequency error. That is, we make a really good guess. On subsequent times that we try and achieve carrier synchronization, we program that known frequency offset into the carrier recovery loop when we start up. So we're starting from a good place. Instead of having to find much of a frequency error, we can just look for the phase error. So in fact, the radio during the initial time memorizes that. And it turns out the algorithm is a little more complicated than it sounds initially because the frequency error that you get is dependent on which channel you're on. Since we're using a phase lock loop with dividers, the amount of frequency error between the two actually changes as a ratio of which channel. So we have to take a combination of the frequency error measured in the particular hop channel that we measured the frequency error on. And when we hop to a new transmit channel, the offset frequency we have to compute as a function of the new channel that we're going to and the frequency error difference. So we have to compute all this on each 10 millisecond hop so that we initialize for every single hop channel at the correct frequency offset. No, the two VCOs are phase locked to the same reference oscillator. So in fact, it only depends on the particular channel and not the VCO itself.
The power up, how many symbols carry that over?
We'll get into that later. The power up is over 100 milliseconds, is over 100 microseconds. So we have a way to do this. Symbol timing recovery, normally symbol recovery locks up tens of times, maybe 100 times faster than carrier recovery. So in general, by the time we achieve carrier recovery, we'll have achieved symbol timing recovery, lockup in the demodulator. Yes, we measure that every hop, and we do a smooth averaging of the frequency error and run that up. We also do, as we'll talk about later, a running average of the epoch timing between the hub and the receiver, so we know the exact time. The modulator is this single IC. This is this Motorola IC that's got all this neat stuff in it. So we take the 300 kilobit stream, we go through the convolutional encoder to provide 600 kilobit, and we take that out in pairs because we have an I channel and a Q channel. These become the two bits that generate our symbols. We differentially encode those between consecutive states. Since we don't have an absolute phase reference, we have a relative phase reference. Those two streams are filtered by this FIR filter. Now this FIR filter has to run at, I think, 16 or 32 times the actual data rate. So there's a little phase lock loop inside here that digitally will phase lock the FIR filter clock to the incoming data stream. It's a clever part. And that allows us to run these filters without having to run a 16 times 600 kilohertz clock into this device. And this has the alpha 0.4 square root raised cosine roll-off. And then those go to the D to A converter. So it's a pretty slick part. From there, the output is up converted. Now there's a lot of ways to describe how a QPSK up converter works. And this is one way to describe it. When I wrote a book, I described it the other way. One way to describe it is that you have one of four possible phase states. Another way is to show that you have two phase states and you generate the output state as the sum of two states. And that's this description here. In this case, for example, we have the I input mixing with the 0 degree signal from an oscillator. And so in the top, in the case of a 1, we can see the sine wave that comes out of that mixer. And if the input is 0, of course, we have the inverse of that. So it's just inverted in phase. If we come down to the Q channel, since we're mixing a baseband signal with a phase reference 90 degrees with respect to the other signal, we can see that the 1 and the 0 are opposites of each other, but they're shifted off in phase 90 degrees relative to the other channel. When we sum two sine waves, we get a sine wave. We don't get something funny, we don't get a double frequency thing, we get another sine wave. And its phase position is just the vector sum of the I and the Q. So in fact, the output is, of course, the square root of 2 times the amplitude of either signal. In terms of the length of that signal, it's just the vector sum of the 2. So that's one way of visualizing the QPSK up conversion process. If we put a 0 in, then we'll sum this vector and that to generate this constellation point. So there's a number of different ways of visualizing this. This is buried inside the Harris part. The oscillator, in fact, is 170 megahertz instead of 85 megahertz, and a divide by 2, and that's how it generates the device. In building this divide by 2, inside this part, Harris had to carefully optimize the phasing, because it's easy to build a divide by 2 where you have almost sine and almost cosine. That is, they're not quite 90 degrees apart. There's a lot of care design in the layout of that divider to get very good phase accuracy between the two outputs. Here's the guts of the receiver. This is one chip, single digital part. And this is, the radio is kind of dependent on a lot of what goes on here. It's all digital, there's no analog. We take the baseband, or almost baseband, I and Q signals, 10 bits each. Now they may be somewhat off frequency, so they could be rotating due to the frequency offset. They come into a complex multiplier. The complex multiplier has an oscillator. In this case, it's a numerically controlled oscillator, so it's got a phase ramp and a sine and a cosine ROM on it to generate the sine and cosine words, and it multiplies those two to come out with the I and Q output. What this does is derotate the constellation. Since we have an analytic signal, sine and cosine, that means that the frequency is either positive or it's negative. We can resolve positive and negative frequencies when we have the quadrature components. And so the purpose of this loop here is to put this NCO on the correct frequency, either positive frequency or negative frequency, that exactly cancels the frequency error of the incoming I and Q signals to result in a derotated I and Q output that is at 0, it's at 0 hertz. So that we don't fine-tune any of the oscillators in any of the radios to achieve phase lock. We do the phase lock via this complex multiplication derotation. So we just take whatever frequency error we happen to get from the crystals in the hopper and the IF stage. We just take whatever they are and we fix it up inside the digital part. Once we have derotated these signals, we have the correct 0 hertz carrier line on frequency signals, and so we have demodulated outputs. We run them through an alpha 0.5 root raised cosine filter, and then we run them into this ROM. And the ROM generates the arctangent of Q over I. What's that? It's the phase relationship. And it generates the square root of I squared or Q squared. That's the magnitude. So we have, in fact, now the magnitude of the constellation and the phase of the constellation at any given point. The magnitude can be used back through an AGC loop, which does a vector scaling of this device here, so that the constellation points come out at a constant magnitude and AGC it. Since we limit the front end of the part, we don't actually have to do this, provided we don't have any significant gain errors. but it is possible to get some AGC range. It's limited in range. It's only about 10 to 20 dB of AGC range here. It's not that much. Harris makes a companion part that you can chain with this, and you can tie the two AGCs together and get about 40 to 60 dB of AGC range. It becomes a compound loop. These outputs come out to a slicer, but it's a soft slicer, in that this device looks at the phase positions and computes the relative phase position to the reference position and outputs a 3-bit level that tells you how closely it is to, how close the eye and the Q points are to the exact constellation points. And these soft bits go off to the convolutional decoder. There's also a symbol error detector. When there are certain conditions met about the symbol timing in here, it'll put out an error that tells you the difference between the desired sampling point of the ADD converter and the actual point here. This then computes the actual clock position error, and this is used to be fed back to those ADD converters, and that's the symbol timing recovery loop in the part. Let's look a little bit about carrier recovery. Carrier recovery is the big thing in a coherent radio. It's probably the single difficult problem. Typically, we look at the phase and we compute an error estimate from the desired phase position to the actual phase position, and that phase error then gets filtered and is used to correct the phase of the numerical controlled oscillator. So it forms a feedback loop which steers that thing onto the right frequency and causes it to all lock up. If that phase is accumulating too quickly, it's hard to grab hold of this thing. And so it turns out we can estimate the frequency error by looking at the derivative of the phase from sample to sample. By looking at how the constellation point is marching around the circle, each sample, we can in fact compute a frequency error term, and that frequency error term overrides or has a much higher gain than the phase error term, and that causes us to quickly slew into frequency alignment, at which point there's no correction and it drops out, and the phase portion of it then takes over. If we're way off frequency, the frequency error accumulates so fast that we can't buff, and then there's a frequency sweeper built into the chip. And in fact, what we do is force a constant number into the numerical controlled oscillator and ramp it up and down. By going through this ramp sweep up and down, finally we'll get close enough to the constellation frequency that all of a sudden the error terms will drop out and the loop will declare lock. There's some digital logic that will switch all of this. It turns out in the phase error detector there are two sets of gain constants, one for acquisition mode and one for tracking mode. We program in the acquisition mode constants, which open up the loop bandwidth so this thing acquires quickly, and as soon as it acquires lock, we snap to the tracking mode. In an analog design, this is almost impossible to do, because traditionally when you go from the acquisition mode where it's wide band, you have really open filter, and you snap it down to the narrow mode, you have residual charge left on capacitors, you have residual analog states that you get glitches trying to do the switch, and generally the glitches will kick you out of phase lock. So it's a tough design. Digitally it's nice because in fact none of those problems exist in a digital implementation. So again, all of this is digital. We have a digital signal I. We look up in the ROM the phase error, which is a digital signal. We filter it with a digital filter. Get a digital numerical controlled oscillator. It's all DSP. There's no analog in here, but it sure looks a lot like an analog implementation. The frequency error phase error determination is switchable from BPSK to QPSK, and how the computation of the phase error term is done. We'll go into that a little bit later. I don't have the details on switching it to BPSK though. If we look at the clock recovery process, clock is symbol timing clock, so this is this 300 kilosample per second or 600 kilosample per second clock. Ideally, we want a transition midpoint on eye closures that happens right in the center. And as we receive zeros and ones, the signals will have zeros, will have ones. But when there's a transition, the transition should ideally occur right at the threshold midpoint. If we're sampling too early on a positive slope, then our sample is before we've gotten up to this transition midpoint. It's happening a little before the peak here, a little before the peak there. And so this distance here is the sampling error, and that's the computed error function for the clock recovery loop. But we have to make sure that we're looking at the correct slope. If we have a negative slope, then again sampling too early gives us the opposite error. So we multiply the error by the sign of the direction of the transition to generate a consistent a consistent value. And then we get the expected symbol values in the transition midpoint. We get an error term when there's a transition that tells us which direction to try and drift the recovered clock. That clock is the clock that clocks the A to D converters feeding this chip. So how does it work? We have the demodulator, and it generates this sampling position error signal, which is a digital word. What we do is we go into a PIC chip. This is the same PIC chip that does the hopping sequence. And we have a numerical controlled oscillator. An NCO is essentially just a register where we accumulate phase. And as we accumulate phase, the phase sweeps up until we overflow, and then it resets down and continues to flip. At this point here, which is the sign bit, we clock the A to D converter chips. As we accumulate error, so we have a constant related to about the desired sampling frequency of the A to Ds. So this phase ramps at just about the right frequency, which is the symbol rate, 600 kilosamples per second. As we have a position error, we modify the phase of this NCO by digitally adding the position error to this constant. And so we'll either speed up or slow down that numerical controlled oscillator. And as you can see, this is now a feedback loop in that we have the position causes an error, the error corrects the position. So in fact, we have a closed loop system for clock recovery. Carrier recovery is a little different. When we receive the constellation, we expect to find 4 samples at the 4 points where the X's are. What we may get at any instant in time, however, may be something that's off phase. So we may receive this constellation point, and that's the error in the received constellation point. The problem is that the error depends on which bit you should have received, and so it's modulation dependent. You need to remove the modulation from the process of determining what the phase error is. To do that, you rotate it by 45 degrees, which will put the 4 desired constellation points on the axis. Then you multiply the error by 4. And what that does is it gives you a phase error in the first quadrant, directly related to the phase error of the signal, independent of the symbol that you actually sent. So essentially, it strips the modulation off and gives you an error term referenced to the 0 phase position. So you get an absolute error term, which is extremely convenient. Turns out to do this digitally is pretty simple. You just add a digital word equivalent to 45 degrees, and then you left shift the word by 2 bits, which does a multiplication by 4. So in fact, digitally it's very simple to do the process. So the carrier error detector implements frequency error term, which is how much the phase rotates each sample. If the loop's too far off frequency, the phase error accumulation increases too fast, we can't lock. We can sweep it. We should only sweep it during the link setup. If we ever get to the point that we're sweeping during the 10 millisecond hops, the war is over. We've lost, because we can never acquire fast enough. So we have to go through this frequency memorization technique, because during the 10 millisecond hop, we don't have time to find the frequency. We only have time to find the phase. Now comes the mathematical part. Those of you who wish to fall asleep may do so now. The way that we analyze a carrier recovery loop for stability, there's a very easy technique called a Z-transform that makes this very straightforward to do. In the analog world, we have a frequency response plane, imaginary, where we have sigma and omega being the complex frequency variable. As we all know, poles on the left-hand side of the plane result in stability. Okay, everybody knows the terrible joke associated with that. The way that you analyze the frequency response of a linear system, time-continuous system, is that you set the frequency variable s equal to j omega, that is the 0 damping point, and you scan the frequency up. And at each point, you look at the ratio of the poles to the zeros. To give you the amplitude, you look at, or the ratio of the zeros to the poles to get the amplitude. You look at the angular contributions of all the poles and zeros to get the phase response. Well, it turns out that in sampled space, sampled time rather than continuous time, we have a neat transform called the Z-transform. The Z-transform is real easy to algebraically write on digital filters. So you can do digital filter analysis about 20 times faster than you can do analog filter analysis. This line, S equals J omega, maps onto the unit circle in the Z-plane. So the origin of this plane, S equals 0, maps onto 1 over Z minus 1. And the region of stability in linear systems maps onto the unit disk in the Z-plane. And this, of course, what this does is it gives us an immediate way to do frequency analysis in the Z domain. It's very simple. What we do is we apply the Z transform by inspection. And all we have to remember is that a register that is something that receives the digital word and holds it for a clock cycle is equivalent to multiplying the word by Z to the minus 1, or 1 over Z. Once we derive the Z transform, or the Z transform function, we can derive the amplitude and the phase by evaluating the transfer function h of z over this unit circle. Just like for a linear system, we evaluated over s equals j omega, we just evaluate over the circle. That circle, since this is a complex plane, is equal to the j omega t. So what we have to do is substitute z equals e j omega t, and then sweep omega from 0 to 2 pi over t. And that will give us one transition to circle. So all we're doing is we're doing the same thing here as we go. We're looking for the ratio of the zeros divided by the poles. Then we look at the angular contribution of each, and we get the amplitude and phase response of the filter. And you can do that in Excel. So Excel has complex numbers, and just like you can evaluate continuous time filters in Excel, you can do Z filters in Excel also. This is the lead lag filter that's in the Harris part. Now, they don't provide any of the math to how to do this. I had to derive all the transfer equations myself, but it was a fun exercise. That phase error signal to derive the carrier position gets filtered. The digital words come in, and they go through a lead stage. And what the lead gain is a constant that you program, and it multiplies the error word by that number and puts out that output and sums it to the output. Then you have a lag section of the filter. There the input is summed with the lag gain. It goes through a register, which is again z to the minus 1. And the output is fed back and accumulated, and that resultant signal goes to the output. And then of course you have the filter clock, so once each error time that you're sampling the error, you clock the register. So that's the filter. How do we compute the filter transfer function? Fortunately, it's just algebra. These kind of things to have feedback loops always drive me nuts. It takes me forever to figure out what the transfer function is. So I busted it into pieces. I got 4 variables, W, X, Y, and V, and we can just kind of write the equations for those by inspection. We got the output here, Y, and Y is the sum of V and the lead gain, K lead, times X, right? We have this symbol V here, and what's V? V is equal to W times the lag times e to the minus 1. So we have V equals K lag W z to the minus 1. What's the signal W? Well, it's just the signal X plus the signal V. Okay? So we've got 3 equations, and we just have to go transform that into the ratio Y over X. So we go through the math, substituting in W's and V's and Y's into the equation. And when we do all of that, we solve for the value Y over X, which is the transfer function of the filter. So what we have is the filter function h of z, which is the digital words you get out divided by the digital words you put in for each clock cycle. And so it turns out the transfer function is the lag filter gain plus the lead filter gain times 1 minus lag times e to the minus 1. It's a very looking equation, but it turns out not to be too hard to analyze. So I put that filter into Excel, and I set the lead value to 20 and the lag value to 0.98. And this is the response of that filter. The blue line is the amplitude response in dB, and the red line is the phase response in degrees. And again, this is just done by taking that equation, evaluating h of z, substituting for z e to the j omega t. So we see that what we have is a filter that's got lots of gain at real low frequency. The gain really falls way off real fast, but comes down. You know, we get about minus 80-something degrees of phase excursion on the filter. We can go into the spreadsheet and just change those parameters and come up with any kind of filter we want to come up with just by changing. The neat thing is that lag function is really an integrator, and the closer we set the lag gain to 1.0, the closer we get to having an integrator function which has got really narrow frequency. So what it does for us, it gives us a real narrow filter with a very simple digital implementation. Now we run into some little complicating things. We had In the phase-locked loop, we had that numerical controlled oscillator that we're multiplying the input constellation by to derotate it. The numerical controlled oscillator converts an error signal to an accumulating phase. That is, if we put a digital number into an NCO, that digital number describes how much gets added to the NCO each time, so that NCO's phase keeps accumulating by that number. What we need to derive is the relationship of the output phase to the input error signal. Okay? This is the way a numerical controlled oscillator works. We have a register, and we have an input, and we take whatever in the register and we add the input to it each clock cycle. So if this number is +1, this thing is going to go up by whatever's in the register plus this amount each clock cycle. So we go through and we can write the Z transform equation here, out equals in plus out times Z to the -1. You simplify the math and you get that the output over the input is 1 over Z minus 1. Interesting result. If we go back to the slide on the S plane and the Z plane, guess where this point is? That's this dot right here, 1 over Z minus 1. Okay? Z minus 1 is the pole, so when Z is equal to +1, you got 1 over 1 minus 1, that's the pole of the system. This point and this point are exactly the same. In the analog domain, a pole of 0 is an integrator. In the digital domain, a pole of 1 over Z to the -1 is an integrator. What's it say? Frequency is the integral phase, okay? Which is exactly the intuitive result that you expect. What does an integrator do? An integrator's got an interesting property. The gain falls off at 6 dB per octave in an analog system. It falls off in kind of a funny shape in a digital system. You get 90 degrees of phase shift all the way down to DC. So what you have is the classic phase lock loop problem. You got 180 degree phase accumulation because you're trying to drive the error between the desired signal and the current signal. 180 plus you get 90 degrees phase in here, so your loop filter gives you 90 degrees of phase to play with. You have to do all of your loop filtering function, and you got 90 degrees to do it in. If you ever exceed 90 degrees, you have an unstable loop. That's the classic phase lock loop problem. Just because we've gone digital, we haven't gotten rid of it. We still have it. So we throw all that together, here's the carrier loop. We have the baseband data coming in, the complex derotator, and the numerical controlled oscillator, the phase error estimation, loop filter. There is a gain in the phase error estimation process. There's the digital words we get out of the phase error have some gain constant Kp related to the number of radians of phase error and how they can map into digital words. So we derive an error signal, we filter that with this filter, we just analyze this lead lag filter to derive the filter signal. So if we go through the math of the output phase function versus the input phase function, I've gone ahead and thrown this number into the NCO. So we have the output phase is equal to N, the transfer function here, times H, the transfer function here, times the difference between the input and the output phase. So the output over the input phase is NH over 1 plus NH, and I go substitute for N, the integrator function of that NCO, and I substitute for H of Z that we calculated from the lead lag filter, and this is the expression that exactly tells us in the frequency and phase domain the characteristics of our carrier. So we modeled that in Excel, and there's a really bad way to do it. If we set the filter constants too high, what we get is a lot of jitter peaking. So we can set those lead lag gains so high that we get 5 dB of gain at a frequency of 0.1 baud. That means noise well removed from the carrier frequency is going to cause the output clock to jitter back and forth, and then it falls off. Very bad choice. This is a much better choice in the track mode. This is the narrowband mode, and here we set the constants. Essentially, the transfer function goes up to exactly 0 dB. That is, if you do it properly, the output phase is the same as the input phase at DC. That is, at 0 hertz removed from the carrier frequency. So you want the output carrier phase to exactly be the same as the input carrier phase. You don't want it to drag behind it by 20 degrees. You want it to be right on. As you get away from the carrier frequency, you can see we quickly attenuate noise off of or away from the carrier frequency. Highly desirable property of phase lock loop filters. The little glitch, this curve is actually a little smoother. This is an artifact of where I computed the points in Excel. What we can see as we go way down the gain curve that we haven't quite achieved minus 90 degrees of phase here. So in fact, we have zero phase. At this point, 0 dB amplitude, so it says the output carrier is in the exact phase agreement with the input carrier. And of course, when we get to half the sampling frequency, all digital filters mirror up on the other side. This is a high-resolution graph of that filter. The blue is the amplitude response, and here you can see that this filter is 3 dB down at 0.0004 baud, so it's a pretty narrow filter. We can actually narrow this up a little bit more. We're running out of dynamic range in the filter if we try and narrow it up very much more. The phase of the filter at the 3 dB down point is about, at the amplitude 3 dB down point is about 15 degrees, so we got plenty of phase margin in the loop. The loop is going to be fairly stable at this point. In the acquisition mode, we go in and change those gain constants, and we can blow that loop bandwidth right out. Here you can see down at the bottom here, the blue line, you can see that. You can see a finite amount of bandwidth, and the minus 3 dB point is out here about 0.003004 baud. That means the filter bandwidth is going to be large, and that filter is going to quickly let us get rid of that phase error and bleed off that phase error. So the way that this radio works is every time it hops, when it first starts up, we program in the known frequency error that we've memorized through previous link setup exercises. We put in the acquisition mode constants into the filter, and the filter starts to acquire. The digital chip actually has the logic to figure out that it's locked, and it automatically switches to the track mode constants. There's no CPU intervention required. It'll do this all by itself. So it'll go into the acquisition mode, find carrier recovery, and lock up into the track mode. And this is the process that's the longest single time event in the radio, each 10 milliseconds. For the last part of the TR analysis, we'll look at the timing. Timing is an interesting problem in TRs. In general, when you have two radios some distance apart, it takes radio time to propagate between the two sites. So for example, if we have a hub-end radio and it starts transmitting, sometime later that signal finally arrives at the receiver related to the propagation delay time. For 20 miles, that propagation delay time is about 110 microseconds. So we transmit for some period of time, and finally the end of the transmission reaches the receiver, and we convert over, and the receiver starts transmitting, and it transmits for some period of time. And if we time this correctly, we will maintain our timing marks here with exact PR synchronization, which means that we can transmit equal to 10 milliseconds minus the propagation delay of the channel. So the transmitter is on slightly shorter than 10 milliseconds by this amount of time. It also means the receiver has this amount of time to recover between when it turns off its transmitter and when it has to start receiving. So we have twice the propagation delay to recover. In this case, about 220 microseconds. We also ramp up the transmitter and receiver, and that gives us a one transmit ramp type. So what that means is the transmit duration on a 20-mile hop is 9.89 milliseconds. The transmitter is ramped up. The Motorola transmit preamp part has a pin that we can run an A to D converter in, and we can hit that thing with a 100 microsecond ramp, so we can ramp the power up and ramp it down at the end of the cycle to try and prevent the generation of any spurious transients at TR switch points. So that the overall timing is the transmitter starts and goes into the ramp period. It takes 100 microseconds. Then there's 800 microseconds for that receiver to acquire carrier recovery lockup. At the same time it's getting carrier recovery lockup, it's also getting clock symbol timing recovery lockup, which happens in parallel. And at that point, we now have valid data bits coming out. Those go into the Viterbi decoder. And our estimate, we're not sure, maybe Phil can help us here, is it take about 60 microseconds for the Viterbi decoder to lock up. I can't remember. It was like about the equivalent of the chain back depth in the Viterbi decoder. So it was about that order of time. So we compute a total of 960 microseconds before that FEC decoder is spitting out good bits after the transmitter starts. And that results in the detailed timing diagram for the radio, which gets pretty complicated. We define the reference timing mark as something that can be easily communicated from the transmitter to receiver. What that mark is, since we're using HDLC frame, we put out a synchronization code, and then we start putting out flags out of the HDLC framer. And when the framer starts sending the first data byte after the flags, the the HDLC controller generates an interrupt to the processor. That interrupt goes and grabs a value from one of the counter timers and says, that's the start of time. And so everybody references their timing epoch off this time here. The receiver now says it knows what time is, and it starts a 10 millisecond countdown from that time. During the link establishment phase, the hub sends to the slave radio or the user radio the reference time, and the user radio counts down 10 milliseconds and sends the exact same epoch mark back to the hub end. The hub end says, gee, that arrived 220 microseconds later than I expected it, so therefore there must be a round trip delay of 220 microseconds over 2 is 110 one way. Therefore, the distance must be equal to 20 miles. And so the hub now knows how far away the user is and what its timing is. And it has the user exactly locked on to a time when that user's transmit packets will overlap with all other users' packets. Since the hub has multiple radios transmitting and receiving at the same time, this allows all users to transmit at exactly the same time into the hub, so that when the hub receives on all channels simultaneously, all the users are in fact exactly transmitting at that time. That's how the timing mark is set up between the hub and the user end. So we have a transmit period. We've got 10 microseconds, which is the transmit time minus the propagation delay. So the receive time, in fact, is slightly longer than the transmit time. Now we have 960 microseconds of receive time up here. We have 100 microseconds of transmit shutdown, and then we have 110 microseconds of either propagation delay. You get the T and the R right next to each other. We just throw away the 110 microseconds. It's idle time. At 10 miles, it'd be half prop delay. We could actually recover this 110 microseconds for 0-mile units, but it was too much trouble for the amount of additional data we get through. So we have a total of 8.83 microseconds of data, and that's where the 8.83 over 10 factor came from in the initial slide way up in the front where we calculated the throughput. That's how much transmission time we actually have working for us. The receiver recovery time then will be 210 to 320 microseconds, depending on how far away the transmitter is. So the timing, the hub establishes the 10.000 millisecond period from its internal clock. The timing epoch is the opening flag from the hub radio transmit frame, 960 microseconds after the transmission starts. The user radio establishes timing by listening to the hub mark, and it smooths the arrival times, because there could be multipath, which jitters this a little bit, so it keeps a running average of the time that it receives the epoch mark. The transmitter ramp up and ramp down consume 100 microseconds each, not 100 milliseconds. The duration is 9.89, and the propagation delay is measured during the link startup, and the hub has to compensate for that delay to get all the users talking at exactly the same time. We have an interesting, we spend all of our time trying to keep people from piling on each other during the pile-up, and here we have a system that in fact encourages it. In fact, it gets all the transmitters to make sure that they only talk at exactly the same time, so it's kind of a counterintuitive approach. Anyway, that's where we are so far with the project, and kind of some of the engineering level analysis that's gone into it. And Greg, from a timing point of view, where are we? Okay, so we have some time for questions and answers, if there are any. Yes, sir. We could program the timing to any limit that we wanted to. This example shows 110 microseconds, but that number can be a constant that we program. However, we know at 1 watt we're just about distance limited at 20 miles anyway, and so what number do you choose? If you choose a longer number, you degrade throughput. If you choose a shorter number, then you limit the maximum transmission distance. Yeah, on a Yagi, on a hub where you have omnidirectional antenna, it's a little tougher. 6 dB is maybe practical. To stretch the link out, you have to increase the propagation delay time, but that's a software constant. It switches from acquisition to tracking mode automatically internally, so there's 2 sets of gain control registers. There's an acquisition set, and there's a tracking set. You've got to load up all those ahead of time. No, there's those are in the loop filter. And so those control the gain of the feedback loop to the complex rotator. So they, in fact, don't change with time. You analyze those once through the Z-transform analysis, you determine what they are, you optimize them for the best performance, and then they never change again. Okay, so that's only a gain control in the feedback loop. I'm not sure. This is time division half duplex, of course, is used in GSM and used in a number of different TDMA systems. This is not quite the same because it's hopping, but the principles are kind of similar to what GSM uses in terms of TR timing. Right. Right, which is set by that propagation timing function. That's correct. Yes, that's correct. Yeah, 3 bits. Beyond 3 bits, you don't get really much more processing out of a convolutional decoder. So it has 3 bits for the I symbol and 3 bits for the Q symbol that it inputs to the unit. The complex up-down conversion, what that's an HFA 3724, I think. It's one of the chips from the PRISM chipset, and it's a very small device. In fact, everything on these things are small devices. They're all surface mounted. DCOs, Bob, I think they made, DCOs are from ZCOM. Yeah, they're just little canned packages that come from ZCOM. Not yet. As we go through testing and find our oopses and fix things, more information will be coming out as we get the pieces ready.
That probably won't be made available or something. It has things designed, and there'll be a lot of design changes.
Right.
Well, I did have capable going on doing all the
They can, yeah, the assembly of this thing is pretty challenging. Some of the parts have 20 mil lead pitches, so they're pretty tough. Yeah. Yeah, we've got, I think in the article that's in the proceedings, there may be some, I'm not sure exactly how many of the parts, but the interesting parts, the up-down converters, Harris 3724, the D-mods, the Harris 5210, and the Motorola part, I don't remember what the Motorola part is. Those are about the 3 or 4 parts that are, kind of big VLSI building blocks. 145.7, MC 145.750 is the modulator chip. Okay. Slides that weren't in the package? No, all the package should have all the slides that were. The last 2 are not there. Well, I guess we'll put those up. Oh, okay. Right. There is no schedule right now on all the.
Next week.
Greg now has a new job.
Weird thing is not, there is no schedule at this time. The group's working on it. Right. We basically got the prototype orders in the last, literally Wednesday before the conference. The group will go back and request that the boards will start building up different sections and testing out the board. Then we'll really know, we'll build base band sections up a little bit at a time, we'll build the CPU up, and then we'll know what has to be checked, what's going to work, what's not going to work. Just as Tom said, we'll know linear real soon. And then once we do that, we'll have a better idea of what the timeline is. But that's just the hardware base band stuff. There's a lot of software that's going to be this time, and let stuff be rolled into place.
Yeah, there's a lot of complexity here.
We'll have something to show me. Don't expect these things to range on.
You guys want to work on the modulator?
I think we got enough to keep us busy now. We haven't priced it out. One of the problems we have is that we've gotten parts in onesie-twosies, and we don't have volume price commitments from suppliers. I hope it's 3 digits.
Oh, 5 or 6, and I'll take checks right now. Just a lot of it depends on the license producer. I mean, now everybody always wants to know how much it's going to cost, what it's going to take. With this type of project, there's so many variables. You know, you've got manufacturability issues, how much are we going to be able to get you buying. Some of the prices are going to cost some of these parts. The lead time on the total stuff is 23 to 4 weeks. You know, there's a lot of issues that are going to require us developing new expertise to go through online. It's not it's not. It's going to definitely be under $1,000. It's very compliant. It'll be more than 100 less than that. Bigger than a bread box, more than a
3 digits. That's engineering accuracy. Okay. Any more questions? Yes, sir. The number of systems that you can put in a hub, the combiner and the linearity of PA is probably going to limit the number of transmitters you can put in the hub. The antennas, we're going to operate this thing, at least in our area, horizontally polarized, to try and avoid all the real strong kilowatt level FM carriers in the 900 meg band. Building an omnidirectional horizontally polarized antenna essentially use a slot type of antenna, and those things get pretty tall and get inefficient when you get beyond about 4 sections or so. So 6 dB is kind of a practical omnidirectional horizontal gain. For a point-to-point link, you can use bigger antennas. I'm no expert on antennas. I don't know what's practical in terms of gain and realism. I mean, bigger antennas is more, but I don't know what a practical limit would be. Yeah. Every time you put another radio in, you've got yet another box to repair when lightning hits the hub site. They're lightning resistant. Yeah, that means they'll resist for the first couple microseconds, and then they give up real fast. Yes, sir. The processor portion has been breadboarded, and our software guy who's not here today has started writing the monitor code, and he's got the compiler and the development environment and stuff on the processor part. So he's off working the Ethernet drivers and all that kind of stuff. So that's the hardware part. The boards you see are like number 1. So we're not very far along. We've done a lot of analysis, but we have no working anything. Okay. All right.
Any other questions, Tom, before we take our 10-minute break and get started on our next session? Any other questions? Okay, we'll see you back here at 12 o'clock.
Each of these transmission times. So even though we're transmitting continuously, we'll be hopping each of those times. We picked 10 milliseconds because it pretty much came out of thin air, but the rationale that we like to explain is that we think it's not going to open a squelch on an FM repeater. So we hope it's short enough that it doesn't actually. It shouldn't anyway. With a 300 kilosymbol per second modulation rate, the spectral characteristics of the emitted signal are going to be so noise-like that no squelch is going to open up on it anyways. But at 10 milliseconds, it's sufficiently fast that we felt it would be reasonably difficult to find for the average amateur. So we'll go through some throughput calculations. In mode 0, which is where we transmit half the time and receive half the time, the raw bit rate is 600 kilobits per second. And because we're running at rate 1/2 coder, the actual user portion of those data bits are half of that total. Then we're only transmitting half the time and we're receiving half the time, so the throughput gets knocked down by another factor of 1/2. And then, as we'll see in the detailed timing at the end of the presentation, there's some overhead inside those 10 millisecond time slots to get the receiver synchronized. And so the throughput is actually about the effective data time of a 10 millisecond frame is about 8.83 milliseconds. And that results in the following throughputs, assuming that we don't have errors on the channel, of 132 kilobits per second in mode 0, 242 in mode 1, and about 425 kilobits per second in mode 2. I guess this is what you call the optimism slide. You can't do better than this. It's pretty useful to have a hub function, and that is, we envision one of the applications of this radio is to put it up at a tall site that ideally has internet access, hook an internet connection into this hub, and then anybody with a terminal can get on and essentially have ISDN speed internet access from their computer, whether it's at home, in their car, whatever. There's also a case, as we'll see, that you might have a good site that doesn't have internet access, and so we have a second application for that. One of the advantages of using time division half duplex is we assign one of the radios as the control radio, and it outputs a timing mark to all of the other radios, so that all the radios in a node, and we can have up to 6 or 7 of these, maybe 10 of these radios, we don't know the number yet. They all transmit at the same time, they all receive at the same time. Which means that we can passively combine the power output of the transmitters, and on receive we can passively split. And then we have to have a little bit of TR switching and a PA to make up for the losses of the passive combiner splitter. One of the difficulties when you combine a number of radios is that your PA needs to be very linear because you're summing a number of carriers. So the peak to average ratio is in fact very high. And so even with a total of maybe 8 or 10 watts, you're probably going to need a PA that's linear up in the several hundred watt range in order to achieve good throughput. You also need a filter and receiver, but the same TR switching signal that slaves all the radios comes out here and runs the TR switches on the PA, the combiner. So what it allows us to do is to build a node by taking a radio and plugging it into a box that sits between the antenna and the radio, and gives us the ability to have multiple users access this device and still not have to get into a real complicated scheme. The benefit of this is that if you have a point-to-point link or you don't want a hub, you just don't implement all of this stuff over here, and so it's a minimal cost for a point-to-point link. So we try to kind of optimize the cost while still providing hubbing function, but you have to implement this RF hardware to do it. The PA can be done in a number of ways. I don't think it's that difficult to switch a solid-state PA that quickly. I could be wrong. Yes. If you try it, yes, it's not really designed for hub-to-hub interconnect. But there are a couple of interesting applications. One is that you may have your internet connection a far distance away from the hub, and so you can assign one of the channels, radio channels, to provide that link back while you have the user channel. In order to use this, the user has to come up and synchronize with the control channel. The control channel then assigns one of the user channels and the particular hopping sequence between the user and the node so that they don't collide with each other. And then the control channel picks the sequences for the other channels so that they stay out of each other's hair. So we felt it was the simplest hardware mechanism that we could come up with to build a multi-channel node. There's a couple of options. One is to have a spreading sequence. It's the same for all the radios, but they start at different offset times so that they kind of leapfrog each other around. And there's a couple of different ways to do that also, some of which have desirable properties. If the radio channels are assigned in a sequence where they're used monotonically, you can prevent any collisions whatsoever, but then you don't have as good statistical properties in the way that you do the hopping. Yes. We look at it. The equipment that we've seen that does that doesn't work very well. In multi-point configurations, it's possible. As we say, it's only software. Okay. However, there may be some practical problems. It's something we can look at to do. Most of the implementations that I've seen have suffered from some fairly fatal problems, so that when you multi-point hub a single radio, the actual throughput drops almost immediately by a factor of 10. Okay, in which case we're back to 9600 baud radio, and why bother to go through the exercise? So, yes. Yeah, the other modes cannot be used in a hub function. You're restricted to mode 0 when you have a hub. That's correct. I guess we could say that was intentional, although it's not, because it allows us to effectively share the internet bandwidth amongst all the users in an equitable way, whether that's intelligent to do or not. It would force them all to get about the same allocation of the channel. Okay, looking at the radio design in particular, our assumptions: transmit output power is 1 watt. This is done so we avoid having to do active power control on the transmitter for the current regulations. I assumed we could build an antenna with a gain of 6 dB at the hub site. An omnidirectional 6 dB gain antenna is quite feasible. 3 dB of cable loss. I assumed a receiver antenna temperature of about 293 Kelvin. The receiver would have 8 dB gain antenna. Since it's probably pointed at the hub, it's a little easier to get more gain. Again, 3 dB of cable loss. The center frequency is 915 megahertz. The bandwidth of the receiver is 600 kilohertz. And the noise figure is 8 dB. Actual, the computed noise figure is 7.8 something. If we do that calculation, of course, we have 2 watts of transmitted power because we got 1 watt and we got 3 dB total gain after you subtract out the feed line loss. The receiver noise temperature is calculated about 438 Kelvin. And this yields a signal-to-noise ratio at the receiver of plus 21.1 dB, which is for QPSK modulation.
Well, next we have Tom McDermott, inside EG, current president of Texas Packet Radio Society. By the way, Tom, congratulations. This is your second year as president.
That's right.
And after starting the organization back in '84, he'll be talking about the FHSS radio design, TAPRs, sponsoring along with the Texas Packet Radio Society.
Thanks, Greg. This talk will be kind of an in-depth discussion of a particular design. One of the problems, of course, you have when you do a design as amateurs is you have to use chips that somebody else invented, and that puts some severe limitations on all the neat stuff you can do. Well, I'll talk about briefly the design objectives, a little bit of the system level requirements. I'll go through an analysis of the system level performance and look at the implementation of this slow hop frequency hop radio, and go into a few of the interesting implementation details. 3 of us, Bob Stricklin, Bill Reed, and I got together a couple of times to talk about what should the design objectives of a frequency hop radio for the amateur do. And we kind of mulled over options, and then we looked at about 10,000 news group postings and sorted through all of those. And kind of came up with a subset of what we thought the design objectives would be based upon what people seem to be asking for. The first one is to provide fairly high-speed throughput compared to what we have today, 1200 baud, 9600 baud. And so our objective was to get something like ISDM throughput, around 128 kilobits per second. There are some options for greater throughput. I doubt they'll be available in the first release of the code, so there'll be subsequent releases. The second objective was to try and provide a path length of 20 miles. Most of the comments we've seen from people is that they'd like to try and get longer path lengths than 2-3 miles out of one of these systems if possible. The third is we dedicated this radio basically to handle Internet Protocol frames. Its whole purpose in life is to move IP frames. So it's a little bit single-minded in that regard. And then minimal disruption of existing users, should say 902 to 928 megahertz. We elected to put it in the 900 megahertz band for a couple of reasons. Number one is that there's already a number of existing Part 15 devices there, and we felt there would be the fewest number of amateurs who would have their aux gored by us putting a product in the band. Consistent with having the frequency low enough, we can actually get a 20-mile path with antennas and feed line that most amateurs would actually be able to implement. And so we elected to put it in the 900 meg band. We'd like to accommodate a reasonable number of simultaneous users, but reasonable is not as large a number as we might desire. How large? Well, we have 43 channels, and we're trying to build hubs that will take up to about 8 or 10 simultaneous users. That's in the multi-point configuration. One of the things we tried to do is, in looking at past packet radio projects, a lot of work has gone on to building point-to-point links, but it really hadn't addressed a lot of the networking problems hams really seem to have, which has to do with how do you build a node that allows simultaneous users to access one good site? How do you provide connectivity of that one good site to an information service that might not be available to the building? We wanted to try and build in some hooks and handles that would make the networking of these radios a little bit easier. The interface to the computers over the Ethernet, that was done because we feel we finally got to the point with things like Windows 95 and NT and Linux that it's actually maybe easier to hook a TCP/IP stack up to a radio through an Ethernet than it would be any other interface. In the future, we'd like to add an EBNO of 18.1 dB. That sounds pretty good so far, but this is at a range of 20 miles. As you can see, there's not a lot of room left over with a 1 watt radio. You're operating pretty close to what you can do at 20 miles with 1 watt. This is free space. If you get into urban conditions where Barry McLaren had a good talk yesterday about path loss in urban areas. The path loss goes up a lot faster in urban areas, and the range is going to be less. If we look at the kind of energy per bit divided by the noise power density that we need for BPSK or QPSK, a bit error rate of 10 to the minus 6 requires about 10.5 dB EBNO. A bit error rate of 10 to the minus 9th requires about plus 12.5 dB EBNO. And that's this point down on the curve. At 10 to the minus 9th, it requires about 12.5 dB. As you can see, we're already, for 10 to the minus 9th, 1 to about 3 dB better than FSK at this point by using QPSK or BPSK modulation. Now, one of the things we have to do is differentially code the data. I may have the wrong factor here. I'll ask Phil. The QPSK data, we actually code the difference between a pair of bits rather than the bits themselves. You lose performance because you have some error multiplication when you do that. And so if you take an error on one bit, it can cause you to incorrectly decode the next bit. And so when you differentially code bits, you lose some loss. I'm not sure if that's a correct 2.3 dB factor or not. There's a factor for the amount of equivalent EBNO that you lose for chaining the calculations. And 2.3 may or may not be the right.
There's actually two things there. There's the error propagation.
Right.
Actually, soft position code is actually not that much. But the error factor can be differentially decoded.
Yes.
It's a different curve. It's an exponential rather than a Gaussian.
Mm-hmm. Yeah, we have a coherent, right, we have a coherent demodulator.
That's not that bad.
Okay, so 2.3 is a little bit too conservative an estimate here. So let's go through the available implementation. We have available an EBNO of plus 18.1 dB at 20 miles. We need, at 10 to the minus 6, we need about plus 12.8, which would yield a raw implementation margin of about 5.3 dB. That's not a lot of implementation margin. We can improve the requirement for EBNO by using forward error correction. We have in the radio convolutional coder using 3-bit soft decision decoding. And that the needed EBNO at a rate 1/2 coder at 10 to the minus 6 is about 5.1 dB, but we lose some for this differential coding. At rate 7/8, we need a stronger signal, but we lose again some from the differential coding. So the implementation margin, if you assume this is a little bit too conservative, is slightly better than 10.7 dB at rate 1/2 coding, or slightly better than 9.1 dB. To me, this is fairly practical. It says that theoretically we could work with 100 milliwatts at 20 miles with no implementation margin whatsoever. Or in a practical case, 10 dB implementation margin assures that we're going to have some reasonable amount of performance at 20 miles. We talked about needing 3 dB of feed line loss. At 900 megahertz, 3 dB of feed line loss corresponds to a pigtail using RG58. It's about 50 feet of RG8, and it's maybe 60, 70 feet of 9913. So you're not talking about a lot of feed line to the antenna here, which means I'll have the IP router into the radio. The radio has sufficient processing capability to do this, and we're in discussions with Phil on the use of his stack, maybe porting his stack over to the radio. One of the first choices we made was to go time division half duplex. And the reason for that is cost and simplicity. In a previous packet system like TextNet, we put in single antennas, single feed lines, and we avoided the use of duplexers and other devices. So we operate half duplex to try and minimize a lot of the antenna infrastructure costs and the RF stuff. We elected to have the radio transmit for 10 milliseconds and then receive for 10 milliseconds. And we have to essentially have a fairly fast TR switching, so it's obviously a solid-state TR switch. And within 10 milliseconds, we have to do a lot of things. And this pretty much determines the throughput of the radios, how fast we can acquire carrier synchronization in the 10 millisecond period. Normally, in what we call mode 0, the time slots alternate between transmit and receive. So it just bounces back and forth between transmit and receive. However, there are times, especially with TCP/IP traffic, where the traffic is asymmetrical. If you do an FTP, you may send not very many bytes to the far end to download a file, and you get a large download. Same with HTTP traffic. And so we wanted to have an option to go into an asymmetrical mode where you may transmit a short time and receive a number of consecutive receive frames, which potentially doubles the throughput of a radio. Yes? No, we'll go into that in detail later on. To look at throughput, we chose to use a QPSK modulation format, and the modulation rate is 300 kilosymbols per second. We may up this slightly because of the exact SAW filter that we happen to be able to acquire, but this was the rate. It happens to match some of the clock rates we have on the module, and so it's an efficient implementation. We transmitted 300 kilosymbols per second, which means that the raw bit rate would be 2 bits per symbol, or 600 kilobits per second. As we'll see, we throw away a lot of those further on. So in mode 0, essentially, the radio transmits for 10 milliseconds, receives for 10 milliseconds, transmits, receives, and just goes on through that pattern. In mode 0, we employ forward error correction, which means that half of the bits are overhead related to forward error correction, and so the effective user data rate is half of 600 kilobits per second times half of the transmit density, so it's about a quarter of the actual raw bit rate. These other two modes are for asymmetrical traffic, where the transmitter will transmit for 11 consecutive times and then receive for 1 symbol time, and the receiver does the opposite. In this mode, we also run the forward error corrector at rate 1/2. We also have a mode, it's built into one of the chips, where we can puncture the code up to a rate 7/8. We lose a little bit of system gain, but we gain some throughput. In this case, we also transmit 11 and receive 0. We picked 11 because we can get exactly 2 maximum length Ethernet IP frames into a single transmission when we do that. One thing that should be noted, the frequency hopper is actually hopping channels each 10 milliseconds, so it's not sitting on one channel for 110 milliseconds. It's actually going to be on 11 different channels during that time. We periodically have to have a reverse channel back so that the receiver can tell the transmitter about the progress and the value of the frames received during each of